give an opportunity, this nice conference. And this is a joint work with Hiroki Kondo, a student. And firstly, I'll give you the background of this work. As already you know, there is a famous correspondence between a category of representation of finite algebra at the negative level and the category of representation of finite UQ gay at the root of unity. It is done by Kajian and Lustig. The main tool for constructing these equivalents, the conformal field theory, more precisely the Bessel-Witte model. And very recently, somehow a logarithmic version of the above this correspondence are considered. And what is a logarithmic CFT? And very roughly speaking, logarithmic CFT is a model of CFT such that something like a KZ type equations have logarithmic singularities. But in mathematical strictly sense, there is no definition. Only physical paper, the logarithmic CFT appeared. So in mathematical sense, there is no definition. That is, there are only some examples in the current situation. As an example of logarithmic CFT, there is a CFT based on the representation of the so-called triplet vertex operator algebra or triplet W algebra, WP. Here P is an integer greater than 2. And the next conjecture is due to Feigin and some collaborators. So there is a log version of Kajian-Lustig correspondence that is as a braided tensor categories, the category of WP modules, category of finite dimensional UQSL2 bar modules. There is a equivalence as a braided tensor categories. That is a conjecture. Here, UQSL2 bar is a restricted quantum group associated SL2, where bold Q is a 2 times piece, primitive 2 times piece root of unity. And they prove that the conjecture for P equal 2 case. In this year, Tsuchiya and Nagatomo proved the following theorem, namely, as abelian categories, these are equivalent. This means this one and this one. So the next problem is this category is equivalent as a braided tensor category or not. And of course, in this category, tensor structure defined by the fusion tensor product, and in this category, the tensor structure is given by a usual tensor product. And in this talk, we only treat the quantum group side. And the aim of this talk, the study tensor structure of UQSL2 bar module, and the following the main result. Indecomposable decomposition of all tensor products of UQSL2 bar module is completely determined in explicit formulas. As a byproduct, we show that UQSL2 bar module is not braided tensor category for p is greater than 3. So it needs some rectification for the Feigen's conjecture. This is a future problem. Oops. So firstly, I introduce some notations. Let p be an integer greater than 2 and bold q be a primitive 2 times pth root of unity. And for integer n, we set q integer in this way. This is a very usual notation. And because bold q be a primitive pth root of unity, this equality is hold for any n. And u bar is equal to UQSL2 bar, the restricted countermeasure 2. This is an associate unitary associative C algebra with generators E, F, and K, and K inverse. And the relation is the follows. These relations and usual defining relation of SL2. Thank you very much. Usual UQSL2 relations. And this one is quite new. K to 2 times P just equal to 1, and E to P and F to P equal to 0. Because of these relations, the restricted countermeasure 2 is a finite dimensional algebra. More explicitly, this is a 2 times P to 3 dimensional C algebra, and the Hopper algebra structure of this one by this formula. This is a very usual definition. So the category of U-bar module of finite dimensional left U-bar modules has a structure of monoidal category associated with this Hopper algebra structure on U bar. And next, I'll explain a structure of U bar module. This is a survey of known result on U bar module, which are proved by these researchers. And firstly, I'll give you a basic tool for investigate the structure of U bar mod. In general, A be an unitary associative C algebra of finite dimension, and this is a decomposition of A into indecomposable left ideals where carry P not equal to carry Pj if I not equal to J. For each I, take a primitive idempotent EI such that A times EI isomorphic to Pi, and set small e sum of all EI. So and define B sub A in this way: E small e times A E is called the basic algebra, which has the following nice properties, namely BA is a Morita equivalent to original finite dimensional algebra A. That is a functor from B sub A mod to A mod, defined as in this way. And since in general, a C algebra B is called basic if B divided by Jacobson radical of B and isomorphic to Cn. It is well known that the basic algebra is described by equivalence relations, and it is easy to show that the basic algebra of A is basic. So what is B sub U bar? Namely, what is the basic algebra of restricted countermeasure 2? The answer is the following. The basic algebra of B sub U bar of U bar is decomposed as a direct product in this way, where S runs over 0 to P, and one can describe each B sub S as follows. If S is 0 over P, just isomorphic to one-dimensional algebra C, and for each S is S 1 dot P minus 1, B sub S is isomorphic to the 8-dimensional algebra B by this Kuiper-Base relation. And there is 2 vertices and 4 arrows. The first and the second arrow in this way, and the third and fourth arrow from this vertices and this vertices, and the following relations. And to get the basic algebra B sub U bar, we need to determine a complete set of mutually orthogonal primitive idempotent of restricted countermeasure 2. So of course that is known, but explicit form is very complicated, so we omit to give it in this talk. So the next problem is, what is the structure of B mod? B is an 8-dimensional algebra defined by Kuiper-Base relations, these Kuiper-Base relations. And in the following, I will give you the complete list of indecomposable B modules and Auslander-Leiten Kuiper of B mod. And we can identify 8-dimensional algebra B module with the following data, namely B plus Z and B minus Z, tau plus 1, tau plus 2, and tau minus 1 and tau minus 2. And here, Vz plus minus is a vector space over C attached to the vertices plus and vertex minus, and tau is a linear maps attached to these 4 arrows. See these arrows, which satisfying the relations that. For a positive integer m and n and I and j, we denote the composition of j's projection and j's embedding divided by Eij. Then any intercomposable B module is isomorphic to exactly one of modules in the following list. The first one is a simple module, and x plus and x minus. And x plus is a module which put plus vertex C, and x minus is a simple module putting C in minus vertices. And the projective injective module P plus and P minus. This is a four-dimensional module of B algebra B defined in this way. Here we put C2 at the vertex plus, and here also two-dimensional vector space put on minus vertices, and arrow means map from this one to this one. And for each integer greater than 2, there is a module defined by in this way. And we put Cn minus 1 at the plus vertices and put Cn on the vertices minus. Here we omit 0 arrows. In this case, zero map attached to arrow minus vertices to plus vertices. Only non-trivial map from plus to minus. And the map defined by these matrices. And M minus is a reversing arrow minus to plus, and same we put same matrices. And W plus and W minus defined in this way. And for each integer n greater than 1, and lambda is a parameter in P1C, E plus and E minus defined in this way. And this module is displayed by these in this way, namely, if lambda is a point in P1C and beta 1, then there is two maps. This J beta n is n times L Jordan cell with eigenvalue beta. And Auslander light and quiver of B module is the following. Here is a X plus and simple module and projective inductive module, and in this another indecomposable module appeared in this way. And how to get this Auslander light and quiver? We divide the quiver B. Quiver B is this one. And we divide the quiver B into the following two pieces, which are isomorphic to the Kronecker quiver, namely Q plus and Q minus. Now consider Auslander light and quiver of Q plus and Q minus. So two copies of Auslander light and quiver of the Kronecker quiver, and paste the above two copies. So we have a Auslander light and quiver of B module. Namely, the green part is a Auslander light and quiver of Q plus, and the red part is Auslander light and quiver of Q minus. Here, M plus is preprojective component of Q plus, and W plus are the pre-injective component of Q plus, and these guys are a regular component of Q plus, and same as Q minus. And paste two copies of Iceland quiver of Kronecker quivers, and at this point, at simple module. So we get Iceland quiver with our 8-dimensional algebra. The next we give a structure of U bar module. Recall a decomposition of a basic algebra U bar in this way, where if for S equal 0 or P, B0 and BP isomorphic to one-dimensional algebra C, and for S1 from P minus 1, BS isomorphic to 8-dimensional algebra B. Denote carry CS, the full subcategory of U bar mode corresponding to BS module for S equal 0 to P. So we have a block decomposition of restricted countermeasure to module in this way. For S equal 1 to P minus 1, and let phi S be the composition of the functors B mode to B sub U bar mode and U bar mode. We'll denote by XS plus, XP minus, X minus, and so on, the image of these modules already appeared above. On the other hand, for S equals 0 or P, let phi S, we use the same notation, be the composition of functors in this way. Let us denote carry X, the unique simple object in C module. We denote the corresponding object in C0 and CP by in this way. So we remark that both XP minus and XP plus are also projective. These modules are simple and projective. In that sense, we sometimes denote carry P sub P upper plus minus instead of XP plus minus. Nextly, we explain a more explicit structure of simple object in each block. Namely, the explicit form of the image of simple module X plus minus by the functor phi S. If S is 1 to P minus 1, XS plus is isomorphic to S-dimensional module defined by basis, and basis n runs over 0 to S minus 1, and U bar action given by in this formula. This is the usual S-dimensional irreducible module. And X sub P minus S minus is isomorphic to P minus S dimensional module defined by basis and U bar action given by in this formula. We remark that since we consider all finite dimensional U bar modules which are not of so-called type 1. So the module which are not of type 1 appeared in this formula, namely, for example, this module is a UQSL2 bar module of type 1, and this one is not type 1 because here is a minus appeared. And if equals 0 or p, xp plus and xp minus, both are p-dimensional irreducible module of restricted countermeasure 2, defined similar way. Of course, p plus is a module of type 1, but xp minus is not a module of type 1. So I mean, this indices means the dimension of simple modules. Other indecomposable objects in CS. Since in curly CS is equivalent to B mode as an abelian category, so all information of indecomposable module in CS can be obtained from one of the corresponding objects in B mode. For example, in B mode, the structure of projective indecomposable module P plus and P minus, we already defined. This is a 4-dimensional B module. And in this way. The structure of P plus and P minus are given in this figure. By easy computation, we have extension, first x1 of from x plus minus to x minus plus, just to two-dimensional, to just have a dimension of 2. So we fix a basis of the x1 and x1 from x plus to x minus and x minus to x plus by a small x1 plus, x2 plus, and x1 minus and x2 minus, respectively. But so we omit explicit form. We omit to give the explicit form, but there is 2 dimension. These are 2 dimension. In the above diagram, we denote, for example, x1 to x2 by the extension of the element of x1b from x1 to x2. The meaning of this diagram is in this way. Applying the functor phi s, so we have a following diagram. So as a corollary, we have, for example, dimension of PS is just equal to 2 times P, because this and this is S-dimensional module, and this and P minus S-dimensional module. And this is a top of PS plus, and this is the circle of PS minus, PS plus. And any information of structure of this module obtained in this way. So any other module, explicit structure of any other module obtained in this way, but we have infinitely many indecomposable module. I omit explicit structure of this module in this talk. So this is a review of known result of restricted countermeasure module. And calculation of tensor product. The main tool for calculation of tensor product is the following. The first one is some basic short exact sequence. This is enough to show the existence of them in B mode, because UQSL2 bar is Morito equivalent to basic algebra B sub U bar. And exactness of functor, this one. This is follows from tensor product over field C. This is very easy to get the exactness of the functors. And for the third, for a projective module P, both P tensor Z and Z tensor P are also projective. And fourth, U bar is a Frobenius algebra. As a byproduct, Z is a projective as if and only if Z is injective. And finally, the rigidity will hold in our U bar mode, namely X sub U bar N Z1 to Z2 times D3 isomorphic to this one, and as a vector space, this one and this one is isomorphic. Here DZ the standard dual of U bar module Z. And it is known that the properties C and D and E hold in more general setting. Namely, for any finite dimensional Hopf algebra A over a field, these properties C and D and E hold in A mode. Of course, B is also satisfied. This is a main tool for calculation of tensor product. Firstly, I'll give you the known result for tensor product of simple module. The following proposition is proved by Lechet-Hintraeff in around 1990s, namely, for S and S prime equal to 1 to P, XS plus tensor XS plus sub S prime isomorphic to in these modules, where delta is 1 or 0, if S plus S prime minus P minus 1 is odd or even. If S plus and S minus S plus S prime minus 1 and smaller than P, this formula is nothing but Krebs-Boltzmann formula. But if S plus S prime minus 1 is greater than P, Krebs-Boltzmann formula not hold, because in our algebra, irreducible module, dimension of irreducible module is smaller than P. So in that case, another decomposition is appeared. And it is easy to see that these formulas, namely simple module times one-dimensional module x1 minus isomorphic to in this one. And by the associativity of tensor products, we can calculate other decompositions. For example, xs minus times x s prime plus isomorphic to this one. And the main result, indecomposable decomposition of all tensor product in U-bar mode is completely determined in explicit formulas. Since these are these are too many, there are too many indecomposables in U-bar mode, we can not list up all formulas in this talk. So in the following, we will give some typical examples. Namely, first, I'll explain the tensor products of ES plus minus 1 lambda with simple module. This module corresponding to lower, how to say, the mouse module in regular component of a Kronecker algebra. Firstly, by direct calculation, we have following proposition. Namely, ES plus minus 1 lambda tensor x1 minus, just isomorphic to this one. And these two formulas ES plus 1 lambda times x2 plus. And this formula are reversing left and right. Since x1 minus and one-dimensional module and x2 plus is a two-dimensional module, so we can compute this decomposition by a direct calculation. And remark that this position tells us in general ES plus minus 1 lambda tensor x1 minus, not isomorphic to reverse first and second decomposition, first and second component, and xs plus times x2 ES plus times x2 plus, not isomorphic to x2 plus tensor ES plus by the formula. So that is to say, U-bar mode is not braided tensor category because parameter is these parameters not coincide. And second, for S and S prime from 1 to p minus 1 and a lambda be a point of this is mistake. This is P1C. Tensor product of ES plus times X S prime plus decomposed in this way. And here I and J are some index set. How to get this formula? Firstly, there is a exact sequence in U-bar mode of this one, and applying this functor and exactness of these functors, we have another exact sequence, this one. And by proposition 4, the proposition 4 is a decomposition formula of simple to simple module proved by Lechetti and Traeff. So we already know precise decomposition of these one and these one. So we have decomposition of this module in this way with an exact sequence, this one, for each T1. And by the existence of these exact sequence, we remark that we know ZT1 is not projective. And assume the formula holds for S double prime smaller than S prime minus 1, then we have the following equality. The first one comes from associativity, tensor product, and the second one comes from a decomposition formula, this part, and third one is also comes from associativity. This formula tells us that the non-projective indecomposable summand of this one must be of the form of this one with t equal p to 1 to p minus 1. Then we have z sub t1 must be isomorphic to this one, since zt1 cannot be projective. So that we have the formula. And another typical example, the tensor product of this one with a simple module. Now, for computing this combination, we need the rigidity. Firstly, we calculate the dual of these modules explicitly. This calculation is comes from this result comes from a direct calculation. And second, dual of these modules isomorphic to this one, and the dual of these modules isomorphic to this one. We will give you the sketch of proof. Since dimension of this one is just equal to p times n, and functor d preserves a direct sum and dimension, so dual of e sub s plus n lambda is an indecomposable module of dimension p times n. This is one of the form this one is or projective. The latter case could occur only if n is smaller than 2. And we compute x1 of these one. Here small x means dimension of x1. And first equality what? First equality. Since x plus 1 is a trivial module, first equality get easy way, and second one is rigidity, and the third one is also rigidity, and this one comes from also rigidity. And since x plus 1 is a trivial module, we have that equality. And final equality, this equality comes from B is a basic algebra of U bar. B is a basic algebra of U bar. And finally, we get from the equality by using calculation in Quiver-With relations. So dual of this one must be the form in this way. By the similar argument, we also compute x u bar 1 and from this one to this one just equal to 1 or 0. So we have dual of these guys isomorphic to these guys. And by using these facts, we have a tensor product and explicit formula for tensor product, this one and this one, in this way. But we have no time to explain how to compute this decomposition. We omit this part. For other combinations, we can compute the explicit formula by similar method by using 5 main tools, namely some basic short exact sequence and exactness of tensor functors, and U-Bayes Frobenius algebras, and rigidity of our categories. As a byproduct, we have the following. Let Z1 and Z2 be UQSL2 bar modules. If Z1 or Z2 do not have any indecomposable summand of type E, is corresponding to regular module in Kronecker quiver, we have Z1 tensor Z2 isomorphic to Z2 tensor Z1. And if P equal just equal to, for arbitrary UQSL2 bar module Z1 Z2, we have Z1 tensor Z2 isomorphic to Z2 times Z1. But if P is greater than 3, there exists UQSL2 bar module Z1 Z2 such that Z1 times Z2 not isomorphic to Z2 times Z1. In particular, UQSL2 bar module is not braided tensor category. Finally, we remark that these methods can be applied only for SL2 case, because if G is not SL2, it is known that UQSL2 bar module has wide representation type. So we cannot list up all indecomposable module in general case. So we cannot apply this method in a general situation, only for SL2 case. Yeah, that end.